chapters that were written. The first chapter that was written about was power amplifiers. First question number 1, identify the type and configuration of amplifier, and I gave you an example. I said there the example is you have to write for these amplifiers below if it's a common emitter, common base or whatever, and what type, class of amplifier, class B, AB or C or whatever, and draw 2 cycles. And remember, please read the question carefully. It says, and draw 2 cycles of output waveform for each of the amplifiers shown below. Normal conditions apply. Alright, so if you didn't get marks, most probably for your output wave, it's because you've only shown 1 cycle, for instance, or you've shown the wrong one, and so forth. Anyway, first amplifier that we can see there is a common collector. If you can still recall, how do I recognize? I go and look where's the input signal applied, where's the output signal taken from. So the remaining terminal is the common terminal for both AC and DC signals. In this case, it's the collector, so it's a common collector. You get 1 mark for that, and of course it's a class B amplifier because no biasing has been applied to this amplifier. So for the sinusoidal signal that's shown, that is what I will see on the output waveform, only the positive alternations for the 3rd mark. Alright, the second one, the amplifier that we started off this semester, common emitter. If I look at the input and the output, and I can see it's biased, it's voltage divider biased. So it's a, most probably, in this case, a class A amplifier, linear amplifier, and I can see my 2 waves on the output shown there. So replica of the input signal, only it is amplified. The third one, when we discussed the different types of amplifiers, remember we've seen the class B, but if I want to get from the class B amplifier, I want to amplify the negative and the positive alternations of my input signal. Then I use 2 methods. This method of course here is the complementary symmetry transistors for 1 mark. And of course it's a class B push-pull amplifier. It's not just a class B amplifier. Now, class B amplifier only amplifies the positive alternation. So it's a class B push-pull amplifier for 1 mark, and we're using the complementary symmetry transistors method. And I can see here on the output waveform that I have my crossover distortion still there. Né? So it's not a class AB. Remember, class AB is the one that is biased as well. Alright, and the last one here, only a small portion of the input signal is amplified. And we know because only a small portion of the input signal is amplified, it is a class C amplifier. And I can see it's a common emitter. Class C, of course, I can see that the amplifier is still negatively biased, so my input signal has to overcome the negative VBB and the 0.7 of the base emitter voltage. Now, so you had to show clearly, because some of you made the mistake to draw this waveform. You've drawn something, oh, this thing is totally out of sync. But anyway, your on time should be much less than the off time, than the negative alternation, so that I can see that it's only amplifying for a small portion of the positive alternation. Because if your lengths of those 2 half of the waveforms were the same, then of course it's not the signal, output signal for a class C amplifier. No. Alright, so for those 4 circuits, 3 marks each, you have 12 marks so far. Please have a look how the marks were allocated. Alright, the following chapter that you wrote about was the field effect transistors. Question number 2.1, graphically determine the Q point for the circuit in figure 1A using the transfer characteristic curve in figure 1b. Show how it was determined in the characteristic curve in figure 1b. Remember I told you when we discussed this during the semester that you have to show me with the broken lines how you determined these values and also write in the values, so the marks will be given accordingly. So as I said here, write down all the values determined on the graph. This was based on basic problem from chapter 8, number 25 for the N channel. Alright, so you would have to go and determined, remember, because it was a self-biased circuit, I haven't got the circuit in here, but it's on your test, it's a self-biased circuit as you can see. And then of course you had to determine the 2 points for the load line. First one was where ID is equal to 0, then of course VGS is also equal to 0. So I can see that my load line starts at the origin there. So 1 mark for that, as you can see. And then you also had to calculate for ID, where ID is equal to IDSS, in this case 10 milliamps, and you get a value of minus 3.3 volts. So you had to show me that on the graph itself as well. There's the 3.3 volts with a broken line. You've plotted the dot there on the next to IDSS. And of course then you connect the 2 points, that's my load line, then you had to write for me, that's the Q point. So you got a mark there for plotting the second point, writing Q, where the Q point is, and also you got the mark for the 3.3 that you wrote there. If you didn't write it there on the graph, because I asked you to write it on the graph, you most probably didn't get the mark. Okay, once you've got that, then of course you had to write in the values of the Q point, approximately 5.9 milliamps. You would see some of you wrote 5.8 or 6 milliamps or whatever, and then I also gave you the mark. Some of you wrote 7 milliamps and 6.9, but of course that's what I said. Please have a look carefully at the scale that's being used. And also for the VGS value for the Q point, minus 1.9 volts approximately. Alright, so 6 marks all in all, given on the graph. Alright. Okay, so that was question 2.1. Question 2.2 was example 8.13 in your textbooks. Name the bias circuit that is used in figure 2, and then you had to name it here at the bottom. Of course, it's a current source for 1 mark. And then if the circuit has to produce a 10 milliamp drain current and a 5 volt drain voltage, what should the values of RE and RD be? And the other 4 marks were allocated as follows. So there's RE calculated, 600 ohms, 2 marks, and RD, 400 ohms for another 2 marks. Question 2.3 was another example, straight from the book. 2.3 for the characteristic curve in figure 2. Calculate the AC drain to source resistance. Ladies and gentlemen, the AC drain to source resistance. A lot of you calculated the DC values. For a JFET biased at the origin of VGS, if VGS is equal to minus 2 volts, assume that IDSS is equal to 2.5 milliamp and VGS off is equal to minus 4 volts. And as you can see there, this was example 8.15. So please make a note in your books if you want to do revision. Right, there's a solution. Formulas from the formula sheet. GM0, you would get then 1.25 millisiemens. Some of you wrote there a small s, which means seconds, of course, which is wrong. And remember that your answers should be expressed in engineering notation. So if you didn't do that, or you scratched out so that I couldn't read, you also didn't get the marks. Then GM was calculated to be 625 microsiemens for another 2 marks, and then RDS is equal to 1,6 kilo ohms. If you wrote 1,600 ohms, then of course you also lost the mark. The instructions were clearly as the same for the first test, and will be for the third test and for the exams as well, to express your answers in engineering notation. Right, question 2.4 is from the textbook, the basic problems again, basic problems chapter 8, number 42B. Find VGS and VDS for the E MOSFET in figure 3. Datasheet information is listed with the circuit, exactly as in your textbooks. And here's the solution. VGS, 2,5 volts, 1 mark. Then you had to calculate K, 888,889 microamperes per square volt, 2 marks. ID, 888,889 microamperes for another 2 marks. And then finally VDS, which is VDD minus IDRD. So a lot of you just calculated IDRD and didn't subtract it from VDD, where you made a mistake, of course. So remember, it is VDD minus IDRD, and you get an answer of 3,667 volts for another 2 marks. Okay, that was the lot. Total marks was 35. Full marks 35 is going to give you 100%.